Okay, with plate tectonics is a theory. It started out as a continental drift theory by Alfred Wagner in 1912, and we later find out this came from the theory. The plate tectonic theory came from the continental drift theory. First thing is understand continental drift theory, that it's only a theory and it was only presented in 1912. By the slides, you can look at the maps, and with the map shown above, it shows the continents that as they are now, but they do look like a jigsaw puzzle than we had before. Alfred Wagner was born, and here's a picture of Alfred Wagner, what he was back in 1912 when he proposed the idea of continental theory in 1891. And he later studied in Berlin and earned his PhD in astronomy, but his field of expertise was in meteorology. He did his explorations to Greenland and other parts to study climate. And later in 1941, he died on one of his expeditions up in Greenland, and his body was recovered later. Wagner proposed that the continents were. It wasn't really until after World War One, or he was injured, was a German soldier for the war, that he really studied and concentrated on his theory, his hypothesis about the continents. He started collecting evidence for it in about 1910, and he didn't propose it until 1912, where he proposed it to a bunch of geologists in a convention, talking about what they were doing. And when he presented this, no one had presented this idea beforehand, and so they had no clue how to handle it. All they did was laugh at him and said he wasn't a real geologist. Part of his theory was the evidence of. Here's a picture of the fossil mosasaurus that they found in Africa and South America. Found that identical fossils located directly opposite on the radically separate continents. What that means is he found a mosasaurus, one of the first marine reptiles, even older than the dinosaurs, were found in both the South American and South African continent. So this led him to the continents. And here's a map of the current of the fossils that were found in each of the continents together at one time. The other part was a leaf, a fossil plant called Geonosopid, and it was found only in the southern continents. And here's a fossil of that leaf that was talked about in the previous. The continents were a supercontinent at one time. So we look at the picture here where the dinosaurs were and see that the continents did fit together, and that these plants were found out through South America, Africa, Antarctica, India, and Australia. Later part of his theory was this, that the rock evidence, the same types of rocks on both sides of the coast, are the same in age. They were formed from South America and Africa, Europe. Similar ages, structure, rock types can be found in Appalachian Mountains on the eastern United States and mountains in Scotland and Scandinavia. We found out later in the fossil record and also in the glacial record that the climate was totally different than what was before, and shows in these pictures that are in these now showing you, it shows that the glaciers were different and where they were located at, and it's showing the fossils where they're at. Mostly in South Africa. In Antarctica, believe it or not, a frozen area had glaciers, had plants. But for glaciers, the percentage with the continents, their current position, much of the world would have been covered in or under ice. But this wasn't the case. Sedimentary rocks examined showed the change in climate and only the possible explanations for the continent drift and movement of the poles. The other part of it was the immense ocean. This is showing the ridges in the world at this time, at this stage. Ridge. The younger rocks were closer to the ridge, and further you got the ridges which supported the idea had the forming of the piece of the continents. And further we have learned as you move from the ridge, the older the rocks get, and the continents become we start seeing in these ridges, mountain ranges, valleys, rifts, they're forming in these regards experts. The oceanic ridges were more direct continents and plate tectonics, as the magma from the core find the weakest in the seafloor through convection currents. It merges through, and a new crust is upon the starts appearing, starts cooling. Lava starts cooling. As seafloor, we started noticing that the seafloor starts going back and forth. It starts from the youngest and starts going to the oldest, to their place. It wasn't until 1960 when Henry Hess from Princeton University proposed that the seafloor itself moves from the central axis and carries the continents with it. This theory is well accepted now, and a phenomenon is known to be caused by the convection currents in the planet. Were very weak in upper mantle or in the lithosphere. Palomagnetism is where we find in the rocks that they are magnetic to where the way they were laid when they were first came out of the earth. Depending which way the true north was, that's the way the rocks facing. And the rocks that we had now are facing where the true magnetic north is. We'll see this again when the magnetic poles switch again and back and forth. So, with recent findings, was Wagner even redeemed for his given credit for his long overdue? He was, in a way. Now we explored the theory, and it was until the 1960s that gave birth to plate tectonics. About almost 50 years after Wagner gave his theory to the geologists, and also after many findings of the continents moving, people started revisiting the idea of plate tectonics and started looking at the floor sea spreading. And so that's what plate tectonics, what we have the theory states. If we look at it, plate tectonics is basically a theory. If you remember right, when I talked about it, that continental drift theory that was developed by after Wagner in the early part of the 20th century gave birth to this theory of plate tectonics. We see now this picture of the world now, and it makes more sense that each continent's on its own plate, and oceans on their own plate, and there's actual micro plates in between. Plate tectonic theory states this: the lithosphere is broken up into plates, or other words called tectonic plates. These lithosphere plates ride on the lithosphere. There are about 7 to 8 major plates and many minor plates. These are 3 types of boundaries that help make these plates move, then create mountains or seafloors: convergent, divergent, and transformant. We'll look at these later. And this is what the world looks like now. Now we go to what forces make the plate tectonics. The main force that drives is under the crust and in the mantle. It is about 3 cells that drive the plates to move. First of all, the convection cell are convection cells inside the mantle. They carry warm air up to the surface, and as soon as they hit the surface, they cool back down, and they repeat this process again. Next, we look at the boundaries that make up the plates and cause earthquakes and volcanic eruptions. There are 3 types of plates boundaries, like divergent, convergent, and transform boundaries. These are the 3 types of boundaries I talked about. A picture of each one. Convergent, there are 2 types. There's oceanic continental, oceanic, and continental continental. Oceanic continental is the crust being subducted under the continental crust and creates mountains, ranges along the coast of western United States. The continental crust is also less dense than the oceanic crust, so this is considerably thicker, almost 25 to 75 kilometers versus the average oceanic thickness of about 7 to 10 kilometers. About 40% of all Earth's surface is known or untrained by the continental crust. The continental crust makes up about 70% of the volume of the Earth's crust. This creates the ring of fire. Here you can see in these pictures the subduction, the oceanic, and to continental. This is what I call the ring of fire. This is mostly in the Pacific Ocean. This is where we have most of our volcanic eruptions and major earthquakes. Take, for example, the earthquake in Tokyo. That was along the Ring of Fire. Examples: Mount Rainier in Washington, Mount St. Helens in Washington, and Mount Rainier. We also have Crater Lake, Mount Zima. We have Lake Hood in Oregon. Both of these are found in Oregon. We have Mount Fuji, Mount Shasta in California, Mount Fuji in Japan. Now we look at continental. The continental collision is two plates that attain a continental crust. One subducts under one continental crust and creates the mountain ranges. We can see this in the Alps in Switzerland and the Himalayas in Asia. Oceanic means you have two oceanic plates going underneath each other, and one's got to give, and one has to go underneath the other. And this is what creates our rift and our ridges in the ocean. This is what creates our rifts in the ocean. Divert boundaries are created in the sea floor. Has volcanic activity. Two plates move apart, away from each other, and this basis fills a new crustal material source from mantle magma that flows below. Examples is the Red Sea Rift, the Great African Rift, and the Mid-Atlantic Ridge. And you can see from here where they work. The Mid-Atlantic Ridge goes right through Iceland, splitting it up so you can live on two continents. And you can see in these pictures how they move apart from each other. Now we get to transform boundary. The famous one of all in the western United States and is found in Southern California is the San Andreas Fault. And this is how they move. They slide back and forth among each other, and they move past each other, left to right. Okay, with plate tectonics comes with mountain building process. You cannot leave part of plate tectonics without the mountain building process. So we have mountains that are formed from these plate tectonic activities. First of all, plate tectonics and mountains are actually together. They actually create the between plates called conclusions. These can happen from continental and oceanic. It is when both plates collide convergent boundaries with the creates of mountain ranges. Cascade Mountain Range. This is where the volcanic rupture takes place. Another one's the Andes in South America, and other mountain ranges in the world. Mountain ranges are basically a series of mountains that solely relate in the orientation of their formation. Mountain systems is a group of mountain ranges that are adjacent called mountain systems. Mountain belts are just part of a larger system. How mountains are formed. There's deformation of the Earth's crust. Mountains can be formed by many ways: plate tectonics, fault block mountains, and other ways. For a few examples, you have the Himalayas in Asia, the Cascade Mountains in California up through Washington, the Sierra Nevadas in California and Nevada, the Wasatch Mountain Range in Utah, southeastern Idaho, and the Rocky Mountains in the western North America. Oceanic crust is where mountains and these are known as island arcs in the ocean. Collision between continents are continents that collide. The Himalayas, the Alps. From this way, the process took place of 65 million years ago, when India broke apart from Africa and Antarctica and became a separate continent, and India started to move up and collide into Asia, and the Himalayas were created. The types of mountains that we see are folded mountains all around the world. Mountain ranges consist of folded mountains when the continent collides. Folded mountains are from tectonic movements, squeeze the rocks layers together: Himalayas, Alps, Urals, Appalachians. We have plateaus that come from the same process of folded mountains, but these mountains are formed by uplifting of the ground. Rivers cut down through the rock layer and create these platoons. Fault block mountains are broken up into large blocks of fault zone causes. These blocks of rocks are tilted and dropped in isolation of their blocks, but they can get narrow valleys from what they are called goblins. Dome mountains are circular or elliptical, almost symmetrical in elevation, structure, and what they classify rock downwards, gently the continental point of floating. And we have volcanic mountains where it's just volcanic leftover from the volcanoes. and we see them on the ground. So basically, that is the whole thing about plate tectonic and about plate tectonic theories and mountain building, because without these sources, we cannot have what we have today. Thank you very much.